Alright, so before we start the new section, I just wanted to take a look at a few exercises that are left over from the previous section. So how about if we differentiate f of x equals x squared e to the 4x times sine of 3x. So you might take a moment to think about that. So the difficulty, right, is that this is a triple product. So how about if we group the first two terms together and differentiate that way? So if we group the first two terms, we'll take x squared e to the 4x prime times sine of 3x plus x squared e to the 4x times sine of 3x prime. Okay, then we can work through the rest of it. The first one will be the product rule. So we have 2x e to the 4x plus x squared. The 4 drops down, right? This is e to the 4x times the derivative of 4x, which is 4, times sine of 3x plus x squared e to the 4x. And then the derivative of sine is cosine. 3x stays there. And then you multiply by the derivative of 3x. Good. All right. So just as kind of a more general rule, what happens if we have e to the f of x power? Then the derivative, this is hopefully you see this as a composition of two functions. E to the x is the outside function and f of x is the inside. So when we differentiate, we'll differentiate e first. So we would just have e to the f of x as the derivative of the outside function times the derivative of the inside function. And just normally we put the f prime out front. Good. How about if we differentiate something like 1 over f of x? Now you could use the quotient rule, but I think it's probably easier to rewrite this using parentheses and a minus 1 power. So this is the reciprocal, not the inverse, right? So this is how we would write the reciprocal. And so now we bring the negative 1 down, just use the power rule. And then we want to follow that with the chain rule. Good. And so if we simplify that, looks like the derivative of 1 over f of x is minus f prime of x divided by f of x squared. Sometimes this is a nice formula to kind of remember, put it in the back of your mind. All right, so how would we differentiate g of x equals x times f of x plus f of x cubed? Well, this first part, we see x times f of x, that's going to be a product rule. And so that'll be the derivative of x is 1 times f of x plus x times f prime of x. The second part is going to be a composition. So f of x is the inside function, so we differentiate the outside function first. And so we end up with 3 times f of x squared, right, times f prime of x for the chain rule. Good. All right. So now we're going to look at something different. And I just wanted to think about this expression up here at the top. What does f of xy equal k represent? And so I've just got a bunch of examples here. And let's see if we can plot these examples. And we're going to plot these examples using Wolfram Alpha. And so let's go into the internet. Here's Wolfram Alpha. And so we can plot these pretty easily here. Just say plot, then x squared plus y squared equals 1. And Wolfram Alpha just takes a moment. And you'll see that it is a circle of radius 1. Now you'll notice one thing about this is what we're trying to get at, is that this curve in and of itself is a curve in the plane, but it does not necessarily represent a function of x, right? Because that would have to pass the vertical line test. And so here the vertical line test fails. So this is not a function. However, if we break apart the circle so that we just take either the top half only or the bottom half only, right, then we can break this curve up into two functions, right? One function again on the top, one function on the bottom. Okay, and so we think of this as implicitly defining a function. It doesn't define a function itself, but it's implicit because we could break up the curve to get a function. Okay, so let's try the next one that's on the list, and that's the x cubed plus y cubed equals 6xy. And let's see what this is going to look like. I wonder what it's going to look like. Oh, that's interesting. So the curve comes down and around and over. So is it possible to break this apart to make this a function of x? Well, you see here, if we follow this curve around, it looks like the curve's coming around this way. It looks like we could use just this part of the function as one part, or this curve right here as one part of the function, and this part of the curve as another function. But you couldn't come all the way down, right? This part would have to be in its own function, right? Because we need to pass the vertical line test. Good. And so this actually defines 3 functions of x. All right. Let's see what this next one looks like. It looks kind of scary, but it's all polynomials. So how bad could it be? Let's see. That's going to be plot y squared minus 1 times y squared minus 4 equals x squared. By the way, do you know what's being plotted here? So what's being plotted is Wolfram alpha is going through the xy coordinate system, right? Plugging in all the points in the xy coordinate system and then seeing if that point belongs to the curve or not. And so in this case, for example, it looks like 0, 1 is a point on the curve. Is that true? Let's come over here. Is y equals 1 would give me a 0 over here, and 0 over here would be, that would make the statement true, right? So the point 0, 1 would be on the graph. We see what other points would be on the graph. How about 0 plus or minus 2 is on the graph? What other points would be on the graph? How about x equals plus or minus 2? If x is equal to 2, then y would be equal to 0, right? Oh, I guess we're not getting that point on our graph. Oh, that's okay. So we're getting a few. So do these functions here, this is just a sample of points here. How many functions of y do you see here? Boy, there's a lot. Here's 1. Here's 1. Here's 1. This would be a separate function. This would be a separate function. This would be a separate function. Okay, you're getting the idea, I think. This is a separate function. This is a separate function. This is a separate function. Okay. This is a separate function. This is a separate function, separate function, separate. Okay, so this defines lots of functions, right? Now, this is only theoretical in that if you were to actually try to solve this for y, you wouldn't be able to. Okay, that's what we mean by we assume that y is some function of x. Okay, because locally we can make it that way. All right. Let's try one more just for fun. They had lots of interesting graphs or interesting functions in the textbook. So these are problems from the textbook. Equals, can you predict what this is going to look like? X squared minus 4. We have a sine of xy. I'm not sure what that's going to look like. Let's see. Wolfram alpha is really having to think about it. Ooh, what? Whoa. This is pretty wild, huh? So once again, this doesn't look like we're getting any functions of y is any function of x. But if you were to zoom into one of these regions, right, you would be able to identify y as a function of x in each of the neighborhoods, each of the little, if you were to zoom in to each of those regions, we'd be able to identify y as a function of x. Okay, so what's the whole upshot here? That what does f of xy equal k represent? Well, f of xy equals k is a curve in the plane, and that curve in the plane can be implicitly thought of as defining y as a function of x. Okay, so f of x y equals k is generally a curve in the plane, and we assume that there are regions of the curve where y can be expressed as a function of x. And that's an implicit way of defining the curve, implicit way of defining y, right? Because y is not actually solved for. And so our main question is, can we differentiate this expression, right, this curve, without actually having to explicitly solve for y as a function of x? And the answer is yes, we can. And the answer is implicit differentiation. So let's just try it out. Here's x squared plus y squared equals 1. And the idea is that we treat y as a function of x. That is, if you want to be really explicit about it, maybe I shouldn't use that word, you could rewrite it like this if you wanted to. And now we're back to a problem that we've already been working with, right? Because to differentiate this, we have to use the chain rule. And so in differentiating, we just have 2x for the first term, and then the y squared, or f of x squared, just bring the 2 down front. Then we have to multiply by the derivative, by the chain rule. And then the derivative of 1 is equal to 0. But then we wanted to find dy over dx, so we could rewrite this as y prime if you want. And then now we can solve pretty easily. Y prime is minus x over y. And so given an expression in x and y, right, this is a curve, we can now differentiate this by treating y as a function of x, and then using the chain rule where necessary. And then we can solve that for y prime. Very good. So we don't need to rewrite y explicitly as a function of x. All right, so maybe we can try another one. Recognize this curve? So again, we're going to treat y as a function of x, but in this case, we're just going to try to differentiate this expression as it stands. So x cubed becomes 3x squared y cubed, 3y prime, or 3y squared times y prime. Did you get that one? So this is from differentiating like an f of x cubed. Okay, and then this one, why do we have 2 terms down here? This is a product rule, that's right. So the derivative of 6x is 6 times the second function y plus 6x times the derivative of the second function, which is y prime. Very good. Oh, well, then we could solve this for y prime, right? So bring the 6xy over, bring the 3x squared over, and then you can factor out the y prime and solve for it. Good. And so there's our formula for y prime. All right, so we'll go through a few more exercises and examples of this, but I think I'll use a different format so you can see me do it live. All right, so this method of differentiation is implicit differentiation. In an expression f of x y equals k, I guess I'm just reading this to you. We assume that y is a function of x, then we differentiate, then we get a formula for dy over dx without first solving for y. Gosh, who put together these beautiful slides? They're available for you on our class website. All right, so the next video we'll try some examples. See you then.